the graph is abundant.
Sorry, I just remembered.
Oh yeah, should I?
No, it's okay. It's okay. I think you can keep just.
Let me. Okay. Let
Yeah,
me
maybe
show
you
the
want
title
to
slide,
just,
right?
Okay, yeah, that's good.
Yeah, this I'm talking about graphs of polynomial growth. This is joint work with Jing Yu, a graduate student at Georgia Tech. Right. So we define this growth function, which is the maximum size of a ball of radius r around a vertex in the graph. Graphs of polynomial growth if this function is bounded by a polynomial. By which polynomial? And in particular, we want to compute the degree of this polynomial. So here's the notation we're going to use, or the definition. And you could define these things somewhat differently. It doesn't actually matter which convention you use, but this is one of the conventions used in the literature. Given a value r, at least one, we define this parameter rho of gr is, okay, so this ratio of two logarithms. What this really is saying is that the value of the growth function at r is equal precisely to r plus 1 raised to this power rho of gr. So this is the exponent, the power to which you need to raise r plus 1 to get the value of the growth function. Why r plus 1? It's purely technical reasons, because I want to allow r to be equal to 1. So for this to make sense, for balls of radius 1, okay, we just we write an r plus 1 instead of r on the base of the exponent. There are other conventions you can choose here, but they all will result in the same theory in the end. And so these exponents are kind of the telling us what is the degree of the polynomial that we need to look at. So we can define what I'm going to call the exact growth rate of this graph as the supremum of these exponents over all the values of r. And this exactly says that the growth function of gamma sub g of r is bounded above by r plus 1 raised to the power equal to the exact growth rate of the graph for every r. And okay, I mean, this is a reasonable definition, but this is maybe not exactly the sort of thing we want to look at, because we really only care about what happens at large scales when we look at vertices that are far from each other in the graph. And from this perspective, the right quantity to look at is the asymptotic growth rate of the graph, which is not the supremum, but the limit superior of these quantities. So eventually, the values, you're bounded by a polynomial of this degree for large enough values of r. Okay, so these are the definitions. Just here they're repeated. Just a few quick remarks. So saying that the graph is of polynomial growth is the same thing as to say that the exact growth rate is finite, and is the same thing as to say that the asymptotic growth rate is finite. So the relationship between these two growth rates is that the exact one is kind of by definition always at least as large as the asymptotic one, and in principle it can be arbitrarily larger. I mean, if the asymptotic growth rate is finite, the exact growth rate is also finite. But other than that, there is nothing we can say. For example, if G is a finite graph, then the asymptotic growth rate is 0. If you look at a finite graph from very far away, right, it just looks like a point. The growth function is bounded by a constant. And this is captured by, say, in this condition that the asymptotic growth rate is 0. But the exact growth rate can, in principle, be arbitrarily large, because some local behavior, just sizes of balls of very small radius, can affect the exact growth rate. Right? If you have a very dense finite graph, exact growth rates will be very large. Okay, and the same with other parameters. You can imagine a graph that asymptotically just grows linearly, but locally there are some dense chunks of this graph which increase the exact growth rate. Okay, does that make sense? Okay, so what are some examples of structures like this? Well, the most familiar example of a graph of polynomial growth is the grid graph, n-dimensional square grid, which I'm going to know as grid by grid subscript n. The vertex set of this graph is just z to the n, and I put an edge between two vertices u and v if their one distance in the one norm is equal to 1. So this is the illustration in the case when n is 2, just the usual square grid, and this is in 2 dimensions. You can imagine an n-dimensional version of this. Somehow, for our purposes, it will be generally more convenient to look at this slightly modified variant of this graph, where we add diagonals inside of all of these square cells. So this is the notation is going to be grid subscript n comma infinity. Infinity because the vertex set is still z to the n, and I put an edge between two vertices u and v if their infinity distance is equal to 1, and this creates all these diagonals within the individual square cells. The reason why we want to do this is because we'll be studying embedding other graphs into grids, and this type of grid is much more useful for this. These ordinary square grids are bipartite graphs, for instance. They don't have triangles, for instance. So you cannot, even given a finite graph, you cannot necessarily realize it as a subgraph of an n-dimensional grid like this. Just because if your graph has a triangle, you cannot embed it into a grid of this form. But you can always embed it into a sufficiently high-dimensional grid with these extra diagonals, because as n increases, these grids with diagonals are going to have large cliques, large complete subgraphs. Okay, what can we say about growth rates for these? So as you would expect, the asymptotic growth rates, regardless of whether you put diagonals in or not, is equal to exactly n. So it captures the dimension of the grid. And the exact growth rate, as you can see, I mean, it's first of all, it's different for these two graphs. The exact growth rates for grids with diagonals is higher, strictly higher than for actual grids. But as a function of n, it's something linear. It's something linear in n. You get some constant factor in front of that. All right. So what are some other examples? Well, these two are kind of a special case of this more general category of groups of polynomial growths. So finitely generated groups whose Kelly graphs are of polynomial growth. And it doesn't, if somehow this actually doesn't depend on the choice of the generating set. So it's either some Kelly graph has polynomial growth, or equivalently every Kelly graph has polynomial growth. And so actually, not only whether or not your polynomial growth doesn't depend on the choice of the Kelly graph, the asymptotic growth rate doesn't depend on the choice of the generating set, although the exact growth rate does. So this again just illustrates that somehow, in some sense, the asymptotic growth rate is a more robust quantity to look at. And yeah, as I said, these grid graphs are Kelly graphs of Zn with different generating sets. And so they show that Z to the n is a group of polynomial growth. Why is this an interesting notion? Because it's sort of one of the most famous results in geometric group theory, where the whole premise is connecting these geometric properties of Kelly graphs with algebraic properties of groups, is this theorem of Gromov's that says that a finitely generated group is of polynomial growth, which is this sort of soft geometric condition, if and only if the group is virtually nilpotent, which is an algebraic property. All right, so these are some motivating examples. So and kind of the story I would like to tell you starts with this conjecture of these four authors. I guess it appears in the paper of Linial London and Rabinovich, but they say that the conjecture is due to Levin. So let's attribute it to all four of them. And what the conjecture is, it's a rather bold statement. They're saying, well, okay, let's take a connected graph G. So this was for connected graphs, which is a polynomial growth, and let's say rho is the exact growth rate of this graph. Then the claim is that G should be isomorphic to a subgraph of a grid graph with diagonals for some finite dimension n. And moreover, these authors conjecture that in fact n should be just linear in rho. So the dimension of this grid should be only bounded by a function of rho, and the function should be linear. So the idea being why linear bound is reasonable here, the hope is that the dimension of the grid kind of captures the polynomial growth rate of the graph, right? If you embed something in a grid of dimension n, your polynomial growth rate has to be at most something linear in n. And if it's rho, so the best you can hope for n to be is to be linear in rho. And the guess was that you can actually achieve that. So this was resolved in 2007 by Krauthgamer and Lee in kind of an interesting way. It turns out that the answer to the first question is yes, but the answer to the second bullet point is no. So specifically, here's what they showed. It's very close to how the conjecture is stated. I'm highlighting the one term that's different. If you have a connected graph of polynomial growth with exact growth rate rho, then it is isomorphic to a subgraph of an n-dimensional grid with diagonals, where n can be taken to be bounded by some constant times rho times the logarithm of rho. And moreover, this logarithm factor cannot be removed. This is actually, in general, best possible bound you can get. So weirdly, the correct thing to do here is not linear in rho, but rho times log rho. Okay, and actually, so let me say a few words about this and where we want to go from here. So how is it proved that the bound is optimal? In some sense, the examples showing that you cannot get rid of this logarithmic factor are sort of not 100% satisfying. They're finite graphs. The examples showing that this logarithm cannot be removed are finite expander graphs, which is sort of a weird situation to be in here, because on the one hand they're finite, right? Which means that they somehow asymptotically, if you're thinking about asymptotic geometry of these graphs, I mean, they should be trivial somehow. But of course, even for finite graphs, there is some difficulty here, because a finite graph needs to still be, if you want to realize it as a subgraph of some n-dimensional grid, I mean, it's still a non-trivial problem. And depending on how dense your finite graph is, the dimension of the grid has to go up. In particular, this is why both the conjecture and the theorem are stated in terms of the exact growth rate. Because if I want G to be a subgraph of some grid, it immediately puts an upper bound on the exact growth rate, not the asymptotic one of the graph. So this is not really an asymptotic. And one thing we may want to do is to turn this into, or come up with kind of analogous asymptotic statement that actually is only looking at the asymptotic geometry of our graph, the asymptotic growth rate. And of course, then you will not be able to make it a subgraph of a grid. You need to relax this condition a bit. And in some sense, the reason why we get this rho log rho is witnessed by these finite graphs that are, I mean, they're expander graphs somehow. On local scales, they don't look like the graphs of polynomial growth. They grow exponentially for locally, but they're finite in the end. So there is some polynomial you can use to bound their growth function, and this is how you get this rho for them, and then you argue that the dimension of the grid has to be higher. Right, so these examples are really, really weird in this way. Somehow completely, in some sense, they kind of miss the point of trying to model the large-scale geometry of a given graph of polynomial growth by a grid graph, because these graphs don't really look like graphs of polynomial growth. Another thing is that if we are trying to model this doesn't tell us exactly, okay, the graph G is a subgraph of some grid, but it doesn't tell us how exactly it sits inside of the grid, right? So this theorem by itself doesn't say that somehow the geometry of the grid, especially on the large scale, is in some sense similar to the metric properties of the grid are similar to the metric properties of the graph you're embedding into it. So it would be nice to kind of strengthen this to have a closer connection between the metric on the grid and the metric on the given graph of polynomial growth we're trying to put inside of it. And another thing that, another question we can ask is, this in particular applies to Kelly graphs of groups of polynomial growth, right? They're connected graphs of polynomial growth. So this means that the Kelly graph of a virtual nilpotent group is a subgraph of just a grid graph of some sufficiently high dimension. It's one of the sort of questions you can ask about these things is, what if you look at now actions of groups of polynomial growth? Can you, in similar way, somehow embed them into actions of Zn? That's to kind of generalize this from just working with groups to working with on the level of group actions. Yeah, so let me summarize. These are the three questions we're asking, which are kind of informal, and I'll make it precise in the next slides, what we want. So first is, can we come up with an asymptotic statement in terms of asymptotic growth rate instead of the exact growth rate? Can we create a more tight relationship between metric structure on the graph G and on the grid into which we're mapping it? And also, can we extend this to a class of graphs that includes, that tells us something about actions of groups of polynomial growth rather than they're just the groups themselves? And the right context of this would be to talk about Borel graphs, which I will explain a bit later. Okay, so let me make these first two bullet points precise, A and B. A nice notion to look at is notion of a coarse embedding here. This is the definition due to Gromov, and it works for any two metric spaces, X and Y. So mapping from X to Y is a coarse embedding if essentially what the definition is trying to say is that the distance between the images of 2 points is controlled in some very loose way by the distance between the points themselves. And to make this precise, we have these two functions, which I'm denoting lowercase b and capital B. It's like a lower bound and upper bound on the distance between the images of 2 points. So let's look at the second bullet point first here, right? It says that if you give me 2 points from the space X, the distance between their images, f of X and f of Y, is bounded below by the function little b applied to the distance between X and Y, and above by the function capital D applied to the distance between these points. And now I need to say something about these two lower bounding and upper bounding functions that makes this non-trivial. So specifically, we want the upper bound to be finite wherever the distance between x and y is finite. We want this upper bound that we get from it also to be a finite quantity. This first clause here, and lower bound should go to infinity. It shouldn't just stay fixed at some value, right? So as the distance between x and y goes to infinity, this lower bound here also goes to infinity, and that's the definition of a coarse embedding. So coarse embeddings don't have to be injective. I mean, they're not actually embedding somehow, but they're kind of asymptotically injective. That's the idea. Specifically, the lower bound here implies that for image of every point, maybe it's many points, but it's a set of bounded diameter, uniformly bounded diameter. So it's like bounded to one function, not quite injective. So here's some pictures to illustrate this. With graphs of polynomial growth. So this is a graph. What's happening here? The vertex set is z, so it's like the one-dimensional grid, and I'm putting edges. Imagine putting edges between two integers if their difference is at most some fixed quantity d. In this picture, I think d is 3, right? So this is a graph of asymptotic growth rate 1, right? It's a linear growth graph. So here's a coarse embedding of this graph into just an infinite line, just this identity function. So here, this map, somehow the distance, the lower bound is just this lower bound function, little b of r is just equal to r. The distances only go up when you apply this function, but they're still bounded above by something that depends on d. It's some kind of linear function. I think it's d times r or something like this. Thinking of as a function of r, it's a linear function of r, where the coefficient depends on what this quantity d is that we chose in the beginning. But I can also do something different. I can collapse. So this previous map is injective. On the other hand, I can make a non-injective function, and kind of by changing the values of these bounds, making the upper bound constant now. So b of, sorry, not constant, but the identity, capital B of r equal to r. And it looks like this: just collapse triples, consecutive triples of points. Split your interval into triples, collapse all of them into individual points, and then there are no edges going. The only edges between these triples that have been collapsed are going between consecutive triples. They cannot skip over. And because of this, so this map is a contraction, right? The distance between the images of 2 points is at most the distance between the points themselves. This is what saying that capital B of r is equal to r means in this case. And we still have some kind of linear lower bound. So this is a different example of a coarse embedding of this type. All right, and so the question we're asking is, and this, well, I guess we're answering this question. It was explicitly asked by Papasoglu, but I think, kind of given the story I've told you, this is a very natural question. Do graphs of polynomial growth admit coarse embeddings into grid graphs? And let me add also, can we control the dimension of the? If yes, can we control the dimension of the grid in a nice way? Okay, does it make sense? So let me tell you what we proved. So this is just the definition of what it means for a function to be a coarse embedding, and the answer is yes to this question. And in fact, we get really nice control over both this lower bound function, upper bound function, and the dimension of the grid to which we have to map. So here's the statement. Okay, and this is for connected graphs so far. I'll return to this question about Borel graphs a little bit later. But let's think about connected graphs. I have a connected graph of polynomial growth, and let rho be its asymptotic growth rate. So I want an asymptotic statement. It's some finite number. Then, okay, I have one extra parameter, epsilon, and you can take epsilon to be whatever you like as long as it's positive. Then I can find a coarse embedding of G into an n-dimensional grid graph with diagonals. So where n is, so first of all, n is something linear in rho. The coefficient here depends on epsilon. I didn't tell you how epsilon is used yet. If you fix epsilon to be something like 1/2, there's going to be a specific constant here times rho. So you get a coarse embedding with n being a linear function of rho, exactly kind of as you would hope it should be. And where is epsilon used? So it's a coarse embedding. What is the lower bounding function, the upper bounding function? The upper bound, b of r, is just equal to r. In other words, the function is a contraction. The distances only decrease when you apply the function. And the lower bound is again is at least some constant times r raised to the power 1 minus epsilon. So it's as close to being a linear lower bound as you want. You can make epsilon as small as you like, so you can make it at least r to the power of 0.999, something like this, right? We would really like to be able to have a genuinely linear lower bound, but our methods don't seem to achieve this. So we have this dependence on epsilon. But at least we can make epsilon as close to 0 as you like, at the expense of increasing the dimension, of course. Yeah. So let me make a few comments. Some of this I already said. So the bounded n is linear as a function of the asymptotic growth rate. So this somehow is the you can think of this as an asymptotic confirmation of the intuition in this conjecture I stated, that graphs of polynomial growth rate rho really kind of are geometrically similar to grids of dimension proportional to rho. That's what's happening here. Yeah, and also this bound on the growth rate means the function is a contraction. On graphs, contractions behave very nicely. They're kind of almost homomorphisms. If two vertices are adjacent to each other in the graph G, then their images in this grid have to be either just equal to each other or again adjacent. That's what it means for a function to be a contraction. So in other words, you're allowed to contract some edges, and the rest of the vertices are distinct from each other. Or I guess every edge can also be contracted to up to an edge. That's what I mean. And yeah, and one other thing, I mean, this lower bound looks kind of strange, maybe. In particular, I have this G in the subscript. This is because I don't want to write out explicit formula for the asymptotic bound on the slide, although we do have explicit formulas, which we're omitting here. Of course, somehow the way this lower bound, okay, as a function of r, this is something like r to 1 minus epsilon, but the constant factor in front of r was, there has to be some dependence on some information about G, just because this lower, I mean, we don't know anything about the exact growth rate of the graph in the assumptions of this theorem, right? So we may have to, so we don't, a priori don't know how big of a sets we have to collapse into individual points to be able to achieve such a coarse embedding. And this kind of is encoded in this constant factor that I'm not telling you what it is, but it's not very complicated. Okay, are there any questions about this before we move on? You can, of course, you can also say, well, can we make this coarse embedding injective? I mean, this function, the way this is described, doesn't have to be injective. It's bounded diameter to 1, but not injective. But you can by tweaking some other parameters, you can make it injective as well. And I'm calling this a corollary because actually it's not very hard to deduce it from the theorem on the previous slide. If you want to get an injective coarse embedding under the same assumptions, the only thing you need to change is this upper bound. If you compare it to this previous statement, here, the function was a contraction. If you want it to be injective, you cannot make a contraction anymore because you have no control on the exact growth rate. So you need to, in principle, allow distances to increase, but you don't increase them too much. You can get this function to be something like a contraction for all large enough values of r. So it's the distance between two images of the f of x and f of y is bounded by either some constant or the distance between x and y. That's what this is saying. Okay, this by itself, this doesn't yet generalize the Krauthgamer and Lee theorem, but if you can again change the parameters to make them exactly as in that theorem. If you can make it a contraction and you can make it injective, and it still will be a coarse embedding, but now things have to depend on the exact growth rate, exactly in the Krauthgamer and Lee theorem. And again, I'm saying this is a corollary because it's easy to deduce from the result in the previous slide. Yeah, so as I said, this is actually a strengthening of the Krauthgamer Lee. Okay, now let me say something about Borel graphs, as I promised. So just to remind you the definition, or at least in this talk, when I say that the graph is Borel, I mean that the vertex set of G is a Polish or a standard Borel space, depending on what category you prefer to work in. It doesn't matter. And the edge set is a Borel subset of the square. So you think of edges as pairs of vertices, it's a Borel subset of VG cross VG. And so kind of a typical example to have in mind, as I said, this kind of is related to studying actions of finitely generated groups. If I have a finitely generated group gamma with a symmetric generating set S, and I have a Borel action of gamma on some Polish space X, I can define the Schreier graph corresponding to this action, which I'm going to denote SCH of XS, where the vertex set is X, the space in which the group is acting, and I'm putting an edge between the vertex X and translate of X by a generator, X and sigma times X, where sigma is one of the generators, and I don't have loop, I don't allow loops, so I only put an edge there if sigma times X is not equal to X. Because it's a Borel action, this graph is Borel, and kind of its components are in one-to-one correspondence with the orbits of this action. And moreover, if the action is free, meaning that non-identity elements move every point, the stabilizer of every point is trivial, then every component of the Schreier graph, kind of by construction, is isomorphic to the Cayley graph of gamma. So this is kind of the case maybe I would like to think about. So then this graph is just a collection of copies of the Cayley graph, one for each orbit of the action, kind of put together into a single space. Right. So as a particular example of this are graphs like this associated with actions of Zn, which are kind of like the analogs of grid graphs in this category. I'm going to call them shift grids. Let's take a canonical action. Let's take the Bernoulli shift of Zn onto the Zn. And this action is not free. Let's pass to the free part. So this is the set of points with trivial stabilizers. I'm going to call it X sub n, just to make the action free so that it looks a bit nicer. And then I define this shift grid graph, subscript n comma infinity, is the Schreier graph on this space where the generators are elements with infinity norm 1. And the point here is that every component is isomorphic to the n-dimensional grid with diagonals. There's some kind of canonical way of constructing a graph like this. So then, if you replace grids by these shift grids, you can, you get a Borel theorem. So what we show is that if G is a Borel graph of polynomial growth with asymptotic growth rate rho, then, and the conclusion is kind of the same as before. For every epsilon, you can find a Borel coarse embedding of this graph G into the shift grid graph, where the dimension is linear in rho, and we have the same lower bounds on the lower and upper bounding functions, little b and capital B, right? So the difference here is that I inserted the word Borel in front of everything and changed the grid graphs to the shift grid graph. So now this graph G is not connected anymore. So you think of this as like a Schreier graph of an action of a virtually nilpotent group, for example. It has one component per every orbit of the action. So of course you could not embed it into a grid graph because the graph is typically, G is typically uncountable, right? But you can embed it into this shift grid graph, and you can get coarse embeddings. And I'm only stating this theorem, but I remember these two corollaries about injective coarse embeddings. You get exactly the same results in the Borel category. I'm not writing them down because this is exactly the same statement. Any questions about this stuff? So you may ask.
I have one question.
Yeah. Mm-hmm.
Oh, sorry. So what distinguishes the shifts grid from just, if I take unaccountably many disjoint copies of grid and infinity, and say distance between different components is infinity?
So very good question. So somehow what's happening here is that there are sort of two independent geometric structures on these graphs that are playing with each other in some kind of way. On the one hand, you can look at the graph metric, and then, as you said, what we have is continuum many disjoint copies of these grids with distances between different copies being infinite. That's exactly what's going on. But the underlying vertex set of this graph actually is a Polish space in this case. So there is this other topology, not coming from the graph, but just coming from the product topology on 2 to z to the n, as the counter space topology somehow. And the key thing is that we want this coarse embedding f to be a Borel function. So if you think of f as a function from vertex set of G, which is this is the part of the definition of a Borel graph, right? V of G is a Polish space. So it has some kind of topology that has nothing to do with the graph's metric again. Well, it has something to do with it because the edge set of the graph is Borel, but the graph metric doesn't generate this topology, right? The graph metric is way coarser. No, the other way around, way finer. And the graph metric gives you discrete topology, I guess, right? So we have that Polish topology there, and we have the Polish topology, the counter space topology on the vertex set of the shift grid graph, and we want a function f, this coarse embedding, to be a Borel function. This is where the whole challenge of this construction kind of goes. You cannot process components one by one because you cannot separate them from each other. That would completely break apart this topological structure of the vertex set. Does this make sense?
Yeah, thanks.
So this is exactly the difference. If I didn't have the word Borel here, then this theorem would be a corollary of the discrete theorem about connected graphs. But with the word Borel, you cannot do this anymore because, like, you cannot use axiom of choice to pick one vertex in each component or something like this. None of that is allowed. The construction has to be somehow uniform and respecting the topology, which is what makes it tricky.
So I guess I have a kind of a vague question. I'm wondering how your results make contact with the problems about like trying to classify nilpotent groups. If there is any contact, I don't know.
I'm not sure. Yeah, this is a good question. Somehow, in some sense, a lot of the difficulty I mean, this is non-trivial and new, even for Schrage graphs of nilpotent groups. But somehow, a lot of the parts of the proof are particularly difficult if you don't know that your graph comes from a group action at all. Weirdly, there are certain auxiliary results we have to prove which were known before for Schrage graphs, but were not known for general graphs polynomial growth. And I'll give you some examples. In fact, starting from this slide. so there are so I mean, I guess there's kind of a question, why do you want to prove this Borel theorem? And I mean, one is, okay, if you want to really, there's this whole program of understanding combinatorics of Borel graphs, definable combinatorics of Borel graphs, and also this kind of, as I said, to generalize something from the level of groups to the level of group actions. But in particular, it actually makes progress on some explicit questions in descriptive set theory and study of Borel dynamics that people have worried about for quite some time. So one notion this is closely related to is hyperfiniteness. What is this? So this is, I'm attributing this definition to Weiss and Slayman still, although neither of these two papers has the word hyperfinite in it, I believe. But I couldn't track down where the term itself appears for the first time. Maybe somebody in the audience knows. But I'm going to say that the Borel graph is hyperfinite if it can be up. So somehow, from the point of view of these Borel combinatorics, graphs that are particularly nice to work with are those that have finite components. If your graph has finite components, you essentially can work with components individually. You don't need to worry about this interaction with the topology that I mentioned. And hyperfinite graphs are those that can be approximated from below by subgraphs with finite components. So a graph is hyperfinite if there is an increasing sequence, a countable increasing sequence, G0, G1, G2, etc., of Borel subgraphs of G, such that each of them has finite components and their union is the entire graph G. So they're kind of exhausted from inside by graphs with finite components. And this is a very classical notion. People have studied it a lot, and there are tons of results about this. But there's also lots of embarrassingly open questions that are essentially as old as this whole area. So one of those kind of famous open questions is about hyperfiniteness of Schrage graphs of Borel actions of groups. And specifically, the question is, what if my group, say, finitely generated? The question makes sense for groups that are not countable groups that are not finitely generated as well. But just for simplicity, let's think about finitely generated groups. The question that was asked by Weiss, is it true that Schrage graphs of Borel actions of amenable groups are hyperfinite always? So why does this make sense? So first, this would really be a classification, yet another definition of amenability, because for non-amenable groups, this is not true. Non-amenable groups can always produce non-hyperfinite Schrage graphs. And on the other hand, we know this is a famous theorem of Ornstein and Weiss. This is true modulo a set of measure zero. So if you fix a Borel probability measure on the vertex set of your graph, and if any probability measure you like, it doesn't have to interact with the graph in a nice way. If you're okay with removing a measure zero set of vertices, then on the rest of it, the remaining graph will be hyperfinite if it's a Schrage graph of an amenable group action. So it's known to be true modulo a set of measure zero. The problem is, do you have to lose a set of measure zero? Can you extend? Can you actually have this construction without referring to measure theory at all? And this has proved extremely challenging. It's one of those questions that are very famous, and many people have thought about them, and we know very little yet. Until recently, this was essentially the only thing we knew, at least in finitely generated case, that the answer is yes if the group was of polynomial growth. This is the theorem of Jackson, Kekris, and Luvo. and so, of course, polynomial growth groups are amenable, but there are lots of amenable groups of exponential growth, for example, to which this doesn't apply. Very recently, there was a really exciting breakthrough, this paper of Conley, Jackson, Marks, Seward, and Tucker-Drob, where they've developed new techniques for proving hyperfiniteness, of graphs in general and Schreier graphs in particular, and they have added to this the list of groups for which we know positive answer a whole bunch of new ones. So I'm not listing all of them because there is kind of a technical condition they need to satisfy. But examples include polycyclic groups, the Lamplighter group, etc. So this includes groups of exponential growth, for instance. So that's really exciting. On the other hand, still very basic questions remained unanswered. For instance, remained unanswered. For instance, this essentially folkloric question: can this theorem of Jackson, Kekris, and Louveau be generalized from groups of polynomial growth or Schreier graphs of groups of polynomial growth to just in general graphs of polynomial growth? Is it true that all Borel graphs of polynomial growth are hyperfinite? And somehow it's a bit weird, but the approach in the Jackson, Kekris, Louveau proof, although it works for Schreier graphs of groups, but it does not work for just arbitrary graphs of polynomial growth. And it doesn't use that much group theory, but it does need to be somehow the proof requires the graph to be kind of uniform a little bit, look kind of the same everywhere, which in general doesn't have to hold for a Borel graph of polynomial growth. And so this is a natural question that I think we will have kind of thought a little bit for a while. And recently Marx mentioned it in his ICM talk, and I'm just quoting him: finding techniques for resolving this question, where there is far less regular geometric structure than in the Schreier graph case, would be one way of making progress towards resolving Weiss's question. I'm not promising resolving Weiss's question, but we can answer the question about graphs of polynomial growth. So it's an immediate corollary of this general result I showed you, that all Borel graphs of polynomial growth are indeed hyperfinite. And how does the proof go? Let's take a Borel graph of polynomial growth. By our theorem, you can find a Borel coarse embedding of this graph into the shift graph for some n. The shift graphs are Schreier graph, by definition, Schreier graphs of actions of Zn, which is a group of polynomial growth. So by Jackson, Kekris, Louveau, these shift grids are hyperfinite. And it's a small kind of standard exercise to see that if you have a coarse embedding into a hyperfinite, Borel coarse embedding into a hyperfinite graph, you yourself must be hyperfinite. So you can kind of pull back hyperfiniteness via this coarse embedding. And so this implies that G itself was hyperfinite to begin with. So in other words, so this somehow is an immediate corollary of our main result, although I should say that actually this isn't the right proof, because we have to prove that Borel graphs of polynomial growth are hyperfinite, or something very similar to that, in the course of constructing the coarse embedding. So in some sense, this is a little bit of circular reasoning here. You actually first have to prove hyperfiniteness, and then you use this to construct coarse embeddings after that. But it is shows that the reason for hyperfiniteness is that Schreier graphs of actions of Zn are hyperfinite. That's why every Borel graph of polynomial growth has to be hyperfinite. And this, since I mentioned that proving hyperfinite is a step in our construction, this nicely allows me to switch to the last part of my talk, where I will say something about just review some of the tools that go into our proofs and constructions, some of the things that we have to prove along the way, which also end up being kind of interesting and connected to ideas from several different directions, several different areas, which I think is kind of nice. So let me show a few of those tools that we use. So one very important concept that plays a role in our arguments is asymptotic dimension, and this is one of those large-scale geometric parameters that was defined by Gromov in his project of understanding large-scale geometry of metric spaces. So there are many definitions of it. I will give you the definition that's the one we actually end up using. So first, a bit of notation. Imagine I have a ground set X, and I have some partition of this set. You should think of it as being a partition into finite sets. That's what it's going to be for us. then I just have this notation x in bracket subscript p. This is the part of the partition containing the element x. You can think of p as an equivalence relation, then this is the equivalence class of x. We use this notion. The definition is a bit technical. I'll show you examples in the next slides. Notion of a padded decomposition. So given a parameter r, an r padded decomposition over a locally finite graph G. Locally finite means that every vertex has finitely many neighbors with m layers. So there are two parameters, r and m. And such an r padded decomposition with m layers is a sequence of m partitions of the vertex set of this graph into finite sets of uniformly bounded diameter. So because G, right, I guess because G is locally finite, this implies that the sets are finite. So there is a uniform bounded diameter of these parts in all of these partitions, all of the parts in all the partitions, satisfying this condition that for every vertex U of the graph, there is at least one of these partitions where the ball around U of radius R is entirely contained in a single part, and the part containing U. So you take a vertex U, you look at this ball of radius R, you have these M partitions. In one of them, this ball is covered by a single part. Okay, again, I'll show you pictures on next slides. But now with this definition, we can define a asymptotic dimension of a graph. The definition can be made more general for metric spaces, but let's focus on locally finite graph case. The asymptotic dimension of a locally finite graph G, A as dim of G, is the smallest d natural number d if such exists. Otherwise, we'll say it's infinite. Such that for every choice of R, I can find an R padded decomposition with d plus 1 layers. So it's, in other words, I have a uniform bound on how many layers I need, what m is in this definition, regardless of the value of R on the radius of this ball that I'm looking at. And you'll see why is it d plus 1 and not d, because we want numbers to look nice. So let me show you an example. The asymptotic dimension of a one-dimensional grid is 1. So one-dimensional grid is just an infinite path, okay? And this is a graph of asymptotic dimension 1. And this picture is supposed to explain to you why. So asymptotic dimension 1, this means that for any given R, I want an R padded decomposition with 2 layers, 1 plus 1, 2 layers. And here's what it would look like. I need to have 2 partitions. One partition is this blue one. I'm splitting into long but intervals of some long but fixed length, just like this, right? And then I do the same thing but shift the intervals somehow. And this is this red partition that's shown on the bottom of this picture. And the point is, if I take any vertex U and I look at a ball of radius R, which is much length, may assume much less than the lengths of these blue or red intervals, then this ball will be contained entirely either within a single blue interval or within a single red interval. Just because a vertex cannot be close both to a boundary of two blue intervals, any boundary between 2 red intervals, because those boundaries are far from each other. And this shows that the asymptotic dimension is at most 1. And it's an easy exercise to show that there has to be at least 1 as well. A more complicated example is a 2-dimensional grid. I will not prove the lower bound for you. It's a little bit harder. But for an upper bound, we're trying to get this padded decomposition. And the idea is that let's do the same thing as we did in the 1-dimensional case, but instead of intervals, let's take squares. So this picture has these big blue squares. Sort of, I'm tiling everything with blue squares, and I'm shifting this tiling now and tiling everything with red squares as well. So now so this is 2 partitions, and I'm allowed to use 3, 2 plus 1, which is 3, right? So why do I need a third one? This picture, almost every vertex here is happy, except vertices that are close to these intersections of blue and red lines. Because those points, if I take a point somewhere here, right, if I take a little ball around it, it will intersect, go between 2 different squares of the red tiling and 2 different squares of the blue tiling. But these are like this one or this one or this one or this one. These are the only locations where we have problems now. And if I add one more, so now I just need to add one more tiling somehow with squares of uniformly bounded size, such that none of those points are close to the boundary of those squares. And for instance, this yellow grid hopefully works. So every point in this picture is is far from the either red boundaries or blue boundaries or yellow boundaries. At least one of the 3. Okay. So more generally, of course, as you would expect, n-dimensional grids have dimension n. And somehow, in some sense, even more general, you can argue that Cayley graphs of groups of polynomial growth have finite asymptotic dimension. And here's the proof. if you're willing, it's the proof is simple if you're willing to use some very heavy machinery from geometric group theory. Gromo's theorem tells us that such groups are virtually nilpotent. It's not hard to see that asymptotic dimension is invariant under taking finite index subgroups, so it's enough to consider just the nilpotent case. And then you can do some kind of inductive argument using the assumption that your group is nilpotent, and this was proved by Bell and Dronishnikov, that finitely generated nilpotent groups have finite asymptotic dimension. So as you can see, this uses a whole bunch of group theory. And indeed, there has been until recently. So I'm citing this not because these people the first came up with the question, but just to emphasize that this was stated explicitly as an open problem in 2019, pretty recently. Do all graphs of polynomial growths have finite asymptotic dimension? There was some partial work in this direction, but essentially this kind of, you know, it was still stuck at the level of proving things for groups or things related to groups. And for general graphs, this was open until very recently. So this was resolved by this large group of people who, in general, made a lot of progress in understanding the asymptotic dimension of graphs. This is a graph theory paper. And the authors care about asymptotic dimension of graphs with different properties, different classes of graphs. And one thing they prove is that graphs of polynomial growths have finite asymptotic dimension. But I'm attributing it to them. But the proof actually mostly, the hard part is proving the Krauthgamer and Lee grid embedding theorem, because using this, you can reduce to the case of Kelly graphs of groups somehow. And in some sense, this is why this is not 100% satisfying, because, for example, there is no nice bound on this asymptotic dimension. You know, it's finite, but for instance, this doesn't imply that the asymptotic dimension of grids or Kelly graphs of Zn is equal to n, regardless of the generating set. And so that has been accomplished by Papasoglu in 2021, who proved this essentially the best bound you can hope for, that the asymptotic dimension of a graph of polynomial growth is bounded by its asymptotic growth rate, which in particular implies the upper bound of n for n-dimensional grids. And in general, this is kind of what it should be. So we work with Borel graphs, so we need a notion of Borel asymptotic dimension. If I'm working with a Polish space X, I'm going to say that the partition into finite sets is Borel if the set of pairs X and Y that belong to the same pair is a Borel set in X squared. There are different definitions you can come up with that would be equivalent to this. The point is that there is a nice notion of Borel, what it means for a partition of a Polish space to be Borel. And it doesn't really matter what the definition is, because we're not going to actually use it. But if you accept this, then in this paper that I already mentioned, where they proved provided new examples of groups, of amenable groups whose trigraphs are always hyperfinite, Conley, Jackson, Mark, Sears, and Tucker Drob introduced this notion of Borel asymptotic dimension, the definition of which is exactly the same as Gromo's definition of normal asymptotic dimension, except for this one word, Borel, in front of the R-padded decomposition. So you have a locally finite Borel graph G, its asymptotic Borel asymptotic dimension is the smallest d, such that for every R, I can find a Borel R-padded decomposition with d plus 1 layers. So Borel meaning that every partition in the decomposition is a Borel partition. And it's kind of clearly, this is at least as large as normal asymptotic dimension, because the requirements are harder to satisfy. The partition has to be Borel. Remarkably, they proved that if the Borel asymptotic dimension is finite, if such an upper bound d exists, then Borel asymptotic dimension and ordinary asymptotic dimension have to be equal to each other. So there are examples where asymptotic dimension is finite, Borel asymptotic dimension is infinite. But as long as you know the Borel asymptotic dimension is finite, they have to be equal to each other. And why is this a useful notion? Because when Borel asymptotic dimension is finite, the graph is hyperfinite automatically. And it turns out to be often much easier to construct these padded decompositions than to prove hyperfiniteness directly. That's how they got all these new examples of groups with hyperfinite trigraphs. What we prove is we prove that actually Borel asymptotic dimension of Borel graphs of polynomial growth is bounded by their asymptotic growth rate. And this somehow is an important ingredient in our construction of these coarse embeddings, because these padded decompositions give us the sort of scaffolding that we use to construct the, for different values of R, they give us scaffolding that we use to construct the coarse embedding. And I should say that because of this theorem here, we only need to prove that asymptotic Borel asymptotic dimension is finite. Then by Papasoglu's theorem, it would be equal to so then by this theorem, it would be equal to normal asymptotic dimension, which is bounded by the asymptotic growth rate by Papasoglu's theorem. But actually, somehow the way our proof goes is just giving this bound directly. And in particular, even for connected graphs, is a different proof of Papasoglu's result. Oh yeah, so I have two more slides to show you. Just another tool, and I'm not going to tell you how we prove this, but one of the key ingredients that we use is the local lemma. So a lot of our arguments are probabilistic. Most arguments that we make in this proof are probabilistic. And what is the local lemma? It's so I will not say exactly what it is because the statement is kind of technical. But I have this picture of this book here just because to illustrate that this is a very common tool in combinatorics. If you do graph coloring or something like this, you use it all the time. If you open any page of this book, you're going to see a use of local lemma there somewhere. And this is some kind of probabilistic existence result. It says that if you want to find a function with certain combinatorial properties, such a function exists if you can verify some inequalities. You compute some numbers, you plug them into an inequality. If an inequality holds, you're in good shape. The function exists. Our problem is that we need the resulting function to be Borel, and somehow this is not at all always possible to achieve. But thankfully, our situation is kind of serendipitous. There is a version of the local lemma that works in the Borel setting due to Choko, Grabowski, Mate, Pehurko, and Terrace. And they have this very strong assumption. It works on graphs of sub-exponential growth. Thankfully, we work on graphs of polynomial growth to which this theorem applies. So we use this theorem several times in the proof. And without it, it would really not be possible to get the result that we want. And okay, so this is the last slide, just to say that there's more stuff that goes into this. I should say that a lot of the arguments that we make are kind of adapted from the proof of the Krauthgamer and Lee theorem, but strengthened or extended or generalized. In order to construct these padded decompositions, we use a ball carving technique, which is common in computer science. I'm giving some citations, but it's been used a lot over the years there. And somehow we use cocycles to encode coarse embeddings. Somehow working with embeddings directly doesn't work, so you need to do something clever with ZM cocycles instead. And this picture here is an illustration of the ball carving construction, artist's impression. But I will not tell you what this means because I'm out of time. Okay, thank you.
Yeah, let's thank Anton. Yeah, well, so are there any questions? I'll just open it up. Just unmute your mic and ask if somebody has a question.
I've got a very, very simple one, which is are there examples of non-immutable groups which have polynomial growth, or is that ruled out by their?
No, right. Every group of polynomial growth is amenable. Yeah. Okay. Every group of sub-exponential growth is amenable. So the definition, a group is amenable if in the scalar graph you can find these what are called Follner sets, which are finite sets whose boundary is an epsilon fraction of the number of vertices in the set. And if your group is of, say, polynomial growth or even sub-exponential growth, just balls of larger and larger radius are going to be examples of such Follner sets. If you're, say, of polynomial growth, you take a ball of radius r. Essentially think of the n-dimensional grid. A ball of radius r has roughly r to the n elements, but the boundary is r to n minus 1, which is a infinitesimal fraction of.
I see. Yeah. So every time you're going to be. Yeah. Right. Okay. That makes sense.
What's interesting is that there are groups of exponential growth that are still amenable. So in exponential growth groups, balls of radius r are not Follner sets, but there are some other sets that work. And I should say this Weiss's question about hyperfiniteness, we know it for groups of polynomial growth, and we know it now for this list of other groups that I gave you, but it is still open for groups of sub-exponential growth, which is kind of the next step. What if I have a group of sub-exponential growth? Then it's still open, even in this regime.
Thank you.
I want to say just thanks for the great talk. It's so interesting that there are so many connections, you know, with like the local lemma and polynomial growth. Yeah, I guess so. So that's the main tool for getting the construction. I mean, I guess I think of the local lemma as non-constructive, although it can be made constructive. But...
Right. So that's the whole point of this Borel local lemma here. That somehow, indeed, local lemma is kind of a non-constructive statement on the surface of it, but there are some contexts in which you can apply it to get something something explicit. And in particular, maybe the kind of the strongest thing, one of the strongest things you can hope for is for Borel constructions to be done using it. And you can do it under the sub-exponential growth assumption, you know, the dependency graph. If you know the statement was local lemma, the dependency graph has to be of sub-exponential growth. And here we're applying it in the polynomial growth case, which is covered by this result. So we're kind of lucky in this sense that the setting we want to work in is exactly a setting in which you can use local lemma to get Borel construction.
Yeah, can I ask you a question? So, you know, Gromov's polynomial growth theorem, of course, is you know, inspired a lot of work, and there's been several new proofs. I'm just kind of curious, is this related to any of these new proofs? Like, are there any, you know, and there's this problem about whether one can get good bounds on the I guess the degree of nilpotency. Anyway.
Yeah, I'm not sure. It would be very interesting. I think it would be very interesting to find to find some relationship between this and proofs of Gromov's theorem, or something like that. But I'm not aware of such connections. But I think it would be really
because I mean, like nilpotent structures don't really show up in what you're doing, I assume.
Right. That's in some sense that's sort of is the point, that we're trying to do things in this as soft a way as possible, precisely because like all of this extent, you know, so like for instance, proving hyperfiniteness, right? As I mentioned, kind of the challenge is, you know, for graphs of polynomial growth versus Schreier graphs of polynomial growth, the challenge is that Schreier graphs are kind of uniform, they look the same everywhere, and these ones can be kind of wild, right? And we don't have any structural information about them. The only thing we know is this bound in the growth rate. That's it, right? This is the only thing we have to work with, and so somehow we're trying to make the proofs as agnostic about the specific structure of the graph as possible, in some sense. This is why probabilistic tools and local lemma become kind of the right thing to use in some sense, because what's great about the local lemma is once you computed the numbers you need to plug into it, you don't need to know what it doesn't care what the structure of the problem is, what it is that you're trying to do. It tells you, yeah, the thing exists, kind of, and you don't need to analyze it kind of precisely or by hand to get the result you want. But I don't think this excludes the possibility of there still being a way of then, after the fact, deducing something about the structure, say, of your Schreier graph or something like this, after you've constructed some, you know, some nice combinatorial structures in it using these techniques. So this is certainly worth thinking about it. I would say.
Maybe a different question. So back to your first result about a coarse embedding into the shift graph, not actually just the grid graph, not the shift grid, where you had some you got a linear dependence, I guess, on.
Well, almost
like a linear,
close to linear.
Sort of, Yeah.
Right.
I guess so if you just drop
it's
this.
interesting to get rid of the epsilon here.
Oh, okay. Yeah, I guess that's kind of what I was wondering. And maybe if you didn't require a specific kind of epsilon bound, like in the lower bound, like what's the best that you could hope for? Do you know? Like, could you take n to be like the ceiling of rho or something? Or is there a reason that that shouldn't work?
Right. Oh, so your question is about the bound on the dimension of the grid. I see.
Yeah. Yeah. Sorry.
Yeah, that is, I think, a very good question. So somehow, and I don't think we have any non-trivial lower bounds. So if you forget about epsilon, for instance, you just want a coarse embedding, say, with some dependence, right? What is the best constant you can put in front of rho? So certainly whatever we get is something that's considerably greater than one. I mean, we didn't try to optimize it, but you lose the constant factor on several separate occasions in the proof, right? And you can ask, I mean, do you need to do this, right? Or not? And I'm not aware of any convincing lower bounds. Part of the reason I think that people haven't given too much thought to the lower bound question, because if you formulate the theorem, in terms of the exact growth rate, as the Krauthgamer Lee theorem is stated, it kind of is clear there is some constant factor, just because the exact growth rate of I mean, that somehow has to do with the exact growth rate of the n-dimensional grid graph. I mean, it's something to compute. Somehow everything is computed up to constant factors there in some sense. But once you start thinking about asymptotic growth rate, I think it makes perfect sense to say, I mean, can you make n be like rho plus a constant, for instance, right? Something like this. Does it have, or like one, rho plus some lower order term? Does it have to be? Does the constant factor in front of rho have to be strictly greater than 1? And I don't know the answer to this. I think at this point it's an interesting question.
Okay, yeah, thanks.
Well, I don't know. I think let's thank Anton again. I've got to be going. So
Thanks.
thanks everyone.
Thank you, slide.
Yeah, thanks for the
Thank you,
great talk.
everybody.
So thank you. Bye.
Bye.